better justice to the issue of coverage testing. In part because it forms an important element of professional software practice, and in part because it forms an important element of today's lab, this week's lab. So I'd like to spend a bit of time discussing coverage from a bigger picture. And really what we're talking about is situating this in the area of systematic testing. So once the code is written, we talk a lot about tester development, about tests that are written for the code, but often once the code is written, we're running a broad set of tests against it, some of which might have been written before, some of which might have been written after the code is created. We might get ideas for new tests based on observation of how the program behaves on other tests. We push it, it seems soft or weak in certain areas, and we write more tests in that area to expose it. So it's a very sort of incremental process associated with that. And note that I'll say we write tests. There is a fair bit of testing that's still done manually. People will go and pound code, as it used to be called. So they'll go and they'll interactively try to break your program. And there's some excellent testers who do that. But increasingly for decades now, we systematically recorded our tests. We created code that tests our program. Why? How do we create code to test code? Okay, yeah, so we can rerun a whole swath of tests. Think about hundreds of tests each new release feature. Or each time our system we've added a new feature, we can rerun hundreds of tests we previously run. Make sure everything is still working with those things, and make sure the new features work as well. And that's going to be called regression testing. We'll also run a wide variety of unit level tests, small low-level tests, for example, that test basic functionality. We can rerun it very quickly after fixing bug, for example. Maybe it didn't work before, fix it, and you can rerun it like that. You don't have to go through and click this, click that, do a refresh, etc. Instead, you just run the test. And these sort of tests can be run if you're going through a UI, like a web type interface, if you're going through a desktop UI, but they can also be run on unit levels, so you're calling a function. What is it that's different? If we're testing a web UI or a desktop UI versus putting the system through its paces by calling functions versus calling one function with different test values, what is it, the name of the element of code that sort of sets the system up for testing? Maybe it calls up a browser to get it ready to go and push buttons through the web on your web interface. Well, and across all those cases, we use a common name for the code that sort of sets the system up for testing. Sets it up so we can test it right away. What is that thing called? It's called a testing scaffold or testing harness. So what differs in these cases is as much the test scaffold as anything else. For web application testing, we might, again, use a framework like web application testing and Ruby or Water. There's many such testing frameworks. For desktop testing one, well, there's one for Java applications, JRobot, and a bunch of others. Abbott and Costello work very closely together doing coverage testing on the one hand and testing through user interfaces. And these allow us to sort of set up these test harnesses that sort of go off and test the system. But we write the tests in code, and we save that code away, and then we can rerun it easily. So that's an important motivation for keeping these things going. We can do so with less human effort. The truth is, though, ladies and gentlemen, that creating the test up front often takes a fair bit of effort. Imagine a system, ladies and gentlemen. Well, think about a system. So you're responsible for an airline ticket ordering system, or you're responsible for the website associated with the bookstore, the booking site associated with the dental office, large dental practice, or a law firm for the document management. Imagine those different cases. If you're working on components for building for a system like that, often what evolves fastest about that system is the user interface. What evolves fastest is not the logic of sort of, you know, how to record, what information needs to be recorded on each tooth that's drilled or whatever for a dental office, or what has to be recorded for, you know, with respect to documents. It's often the user interface that evolves the fastest. The user says, you know, I don't like how that looks. Can you go change that? And that often iterates very quickly. So one of the things you have to watch out for with automated testing, with test code, is that your test breaks. You have them testing and pressing that button and filling in these fields, and suddenly there's a different number of fields, and the button is now been thrown anyway. Suddenly you have to change your test. So this is the downside of testing. It's easy to think it speeds everything up, but often it takes a fair bit of time up front and a bit of time to evolve it. Okay, so systematic testing is, a lot of it is done, and sort of most of it is done after we've written the code. And we're going to be talking today about some elements associated with test coverage. And really what test coverage deals with is the issue of thoroughness of testing. How, ladies and gentlemen, can we have confidence that a program works? How can we raise our confidence that a program works? Okay. Yeah. Throw everything out, and that includes things that are legal, includes things that are illegal. And sometimes users do things that are illegal, try to say, save without having filled in all forms, right? They mistype the credit card number. It's an illegal credit card number, but you can't just crash. You've got to make sure that it gives them appropriate warning, or otherwise handles it gracefully. It doesn't order the book. They haven't given a proper number. And it doesn't charge the credit card if they've given it a proper number. For sure, because it doesn't know the full number, but it needs to do something which warns them. So, you know, testing coverage is one way to try to speak to the issue of how thoroughly have we covered the system. Turns out it's not the only way. We may take a look at a test matrix later in the class, but it's one of the most popular ways coverage, and there's this wide set of coverage tools out there. Covertura, for example, I mentioned several before, working for UI testing and for coverage, and there's a variety of them elsewhere. Now, when we're talking about test coverage, how much testing we have accomplished in a program, we can talk about testing at different levels. What fraction of the paths through the code we test? Turns out that's rather slippery. For most programs, there is an infinite number of possible paths through the system. You can go around the loop once, or twice, or 3 times, 4 times. It's an arbitrary collection, I should say, but we might reason about how many different sort of threads or programs we accomplish. In the sort of code that you're seeing, you can actually reason on it. Statements in the code. What fraction of the statements in the code, the things like an assignment, or the things like a function call that's made, or the things like an increment or an if statement, what fraction of those have we reached? Why might we care about that? Why do we care whether we've reached the statement or not? So maybe we have a statement. Learned my lesson last time. I'm not going to depend heavily on your knowledge of pointer arithmetic, but if we have some statement like this, you're comfortable with that, right? We have a pointer. This is a pointer. Maybe it's into an element of an array. Maybe it's a pointer to some memory that's been allocated for some structure. So we have this pointer, and we assign to the whatever it's pointing to. So here we have this pointer, and it's pointing off to some bit of memory, depending if it's a character pointer. This is character C, depending if it's an integer pointer. This could be about 100 or whatever. And by assigning to star P, we change the value. Maybe foo returns, returns the value 0, so we put a 0 there. Maybe foo returns the value 1,000, we have 1,000 there after the statement. So suppose that the code never reached that statement. Is that, why do we care in terms of testing? So it never reached that statement. Who cares? Good. So how do we know that this thing is going to do the right thing? After all, it's presumably it has some job, some purpose, some meaning there, and if it doesn't, there's no reason to include it in the code base. So presumably it was put there for a reason to accomplish some task. How do we know it accomplishes the task for which it was designed? How do we know, for example, that something bad won't happen here? What bad thing might happen here? You got a null pointer exception. Maybe once we hit this point, the program will blow up, crack. Is that a bad thing in terms of severity? Yeah. It's bad. It's bad. Bad. So null pointer exception is not a good thing. And if we don't reach the statement, how do we know that that won't happen there? So statement coverage, we're saying, okay, here, what fraction of statements have been reached? Suppose our testing did reach here at some point. Suppose our testing reached this point. Is that a guarantee that this is correct? Why not? Yeah, foo might return the wrong value. Maybe foo always returns 0. And it's supposed to compute the 50th Fibonacci number. It's supposed to go out and grab the weather from a website and return the current temperature in centigrade or something. And all it does is it's broken. It can't even get to the website or whatever. And it doesn't even go to the right website. So there's no guarantee because we have reached it that it's accurate, but hopefully we're looking at outputs that are influenced by this that would tell us, okay, is it working? Is it actually retrieving a meaningful temperature, for example, from the website? So if we haven't reached this, we've left the door wide open to bugs. If we have reached it, we haven't demonstrated it's correct yet fully, but we may have some evidence to the fact to lend some confidence that it's correct. And we verified that it doesn't, at first run, lead to a null pointer. So we've ruled out some obvious, super crude failures because of it. But coverage doesn't mean correctness always, but without coverage, we can't have a hope of saying that the program is correct. Okay, so it's a necessary but not sufficient condition for correctness, coverage is. Is another way to put it? Okay, so statements about functions in code. Why would we test a function? Well, if foo is being used in our code, and we've never actually seen a call to foo being used, we can't know if foo is working correctly as a whole, right? Never mind going into all the gory details about how foo works. I mean, if we've never even called it, we can't claim without a red face that it's working properly. Can't pass the red face test. Conditions. If we ever tested this program where the branch is true, the branch is false, we're not going to be able to make a strong statement that we've really tested this one. States the program. This can be a higher level state, so if the system is in this broad state, it's in insert mode. It's not in insert mode. It's in a mode where it's signaled an error or what have you. It's in a mode where the document has been modified versus where it's read-only or what have you. Then possible inputs and possible outputs. We might want to say, okay, we've tested it with an input where, you know, we've said that this person is not married and this other person is married, possible inputs there, and possible types of outputs. I'm not going to be talking about this at all these levels of detail, but you should be aware that coverage goes on at many different levels, okay?